YouTube page. Yep, so from now on, everything we do is recorded. So you know the drill. So thank you very much for everyone who's here today, especially our two speakers. Today our team is nuclear fusion, and we will be listening to very interesting talks by Elliot Lambert Parsons from the UK Atomic Energy Authority. Hi, Elliot. And Prashant Dwivedi from the Czech Technical University in Prague. Hi, Prashant. And they will give talks about their research projects and will be available to reply to any questions from the audience during our panel session that will start after all the presentations have been delivered. And the webinar today aims to promote a great discussion around nuclear fusion and promote wonderful research and cutting-edge techniques like the ones they're using in their work every day. So with no further ado, let's introduce our first speaker. So our first speaker is Elliot Lambert Parsons from the UK Atomic Energy Authority. Previously, Elliot studied at the University of Sheffield. He then joined the graduate scheme at the UK Atomic Energy Authority as a mechanical design engineer. And Elliot now lives in Oxford and works on the UK AEA Centre for Fusion Energy site in Colham. So Elliot, thank you very much for accepting our invitation to join us today. And whenever you're ready, the stage is yours.
Okay. Am I sharing now?
Yeah, that's perfect.
Okay. So as Anna just said, my name is Elliot, and I'm a graduate mechanical design engineer at the UK Atomic Energy Authority. I'm going to be talking to you a little bit about STEP, which is one of the projects I'm working on. It stands for the Spherical Tokamak for energy production. So first of all, what is fusion? At UK Atomic Energy Authority, our mission statement is to lead the delivery of sustainable fusion energy and maximize the scientific and economic benefit. Fusion is a reaction that's taking place every day in our sun, and it's the combination of hydrogen isotopes to produce helium. So this takes place at extremely high temperatures. In the sun, it's around 15 million degrees Celsius, but because that has the mass of the sun to aid with that reaction, we actually need to do even hotter than that here on Earth. So we create a plasma, which is 150 million degrees Celsius on our site in Cullen. And obviously there's no materials that can hold this sort of temperature in a closed vessel. So we have to use magnets to contain our plasma. And that's what we do down in Oxford at JET. So this is JET. If I was in the office right now, it would be about 400 meters away from me, but unfortunately I'm not at the moment. But this is JET is the Joint European Torus. And torus is just the donut shape of the reactor. And Joint European because there's multiple European agencies that are feeding into this project and have been for many years. So JET is a tokamak, which is a magnetic field used to contain plasma in the shape of a torus. So any vessel in this setup is also a tokamak. There's one being built in France at the moment called ITER, and STEP is also set to be a tokamak as well. However, it will be a spherical one rather than a donut configuration like this. So what does JET do? Well, JET is already producing fusion. So why do we need STEP? JET at the moment can only produce a negative Q factor, which means that it's producing less energy out than it's producing in. And the aim of STEP is to get this value positive. So it's the world's first commercially viable fusion plant. But it's important to note that even though it's commercial, it is only a prototype. So we're going to be proving that we can produce electricity using fusion. However, this energy won't be going to the grid or powering any houses or anything at the moment. And we will also need to demonstrate that there's a net electricity output from this reactor. There's also challenges in remote maintenance that have not yet been faced pretty much anywhere in any reactor in the world. it's a highly radioactive environment, which means we can't put manned personnel in the buildings. So we need to use robotic manipulators to perform maintenance tasks. Even this has its own issues, as radiation can be really damaging to electronic components and diagnosis. So it's about figuring out how we can use robots in those conditions to carry out the maintenance tasks that would normally be carried out by humans. There are also some cranes in this building that are likely to be the biggest cranes that have ever been produced on Earth. I think there's one that's going to be spec'd up to about 4,000 tons. So as you can imagine, that's absolutely massive, and it's all really pioneering stuff. So this is the timeline for STEP. We're currently in the concept design phase, which finishes in April next year. And then we'll progress into the detailed design and mobilization stage from 2025 to 2035. So this will be detailed dimensioning of reactor components and engineering design. We'll be finalizing our maintenance strategies and coming up with potentially early manufacture of prototypes and tokamak components. So after that, we'll then go into the main construction of the plant. So the buildings will start coming together, the reactor hall, everything like that. And in 2040, we hope to commission and begin operations. And that will start off with helium plasma cycles and progress onto deuterium tritium cycles. So these are the STEP performance goals. As I mentioned before, it's looking at a positive Q factor, which is where fusion power out is higher than required heating power for the fusion reaction. So anything over Q factor 1 is positive. However, if you look at the diagram on the right, you can see there's many losses from getting that fusion power into actual net electricity out. The tiny arrow down here is the net electricity out, and that's set to be 133 megawatts, even though we're producing 17,000 megawatts in fusion power. So for this reason, we're going to be looking at a Q factor of around 30 to allow for these losses through like things like the turbines, cryogenic cooling, and recirculating heat back into the reaction. There's also a goal for STEP to have a positive tritium breeding ratio. So in the reactor, we have these vessels called breeding blankets, and they're essentially lithium housing vessels. And as the neutrons pass through the lithium from the fusion reaction, we can actually breed tritium, and then that tritium can be reused for the DT fusion reaction. And the aim is to produce more tritium in the breeder blankets than we use for the reaction, so that the vessel can be self-sustaining. So this is the STEP reactor here, and these are the main components. There's the bioshield lid at the top, which is used to contain the radiation and stop any leakage into other areas of the facility. Then there's the cryostat lid, which is the barrier to contain the cryogenics. So within this area of the vessel, you've got the cryogenic magnets, which are operated very close to absolute zero, and cryogenic pumps to provide the vacuum. The fusion reaction has to take place in an ultra-high vacuum, as other molecules and particles in the air would interfere with it. So that's where the vacuum vessel comes in. The magnets, as I mentioned earlier, are used to confine the plasma, to keep it away from the first wall of the reactor and prevent damage to the insides of the tokamak. The breeder blankets are used to produce the tritium, and the diverters, which are at the top and the bottom, labeled upper module and lower module, are used to divert plasma away from the central reactor and collect dirty particulates and dust. Okay, I'll show a short video about the maintenance task, which we're going to carry out on STEP. So this is a 17-ton articulated lorry and a human for scale for the size of the facility. And as you can see, once you zoomed out, they're pretty much invisible. So that should give you an idea of the scale of this thing. It's split into two halves, the Tokamak Logistics Center and the Tokamak Hot Cell. The Tokamak Hot Cell is what houses the Tokamak reactor, essentially a bioshield around it. These are all the section components which I went through before. So there's three maintenance regimes we're looking at. long-term maintenance, which is a full restructuring of the reactor, which will take place every 4 years. Another long-term maintenance for every 2 years to replace the central column magnets, and short-term maintenance every 6 months, which will be done through radial access ports, and is mostly for repairs and resurfacing areas. So for the main maintenance strategy, the 4-year one, we'll have the components come in ready for the replacement. Then, as you can see here, bioshield lid comes off. Then a trolley will come in. That's the cryostat lid that will be taken away to a high activity cleaning area. The cryostat lids and some of the exterior magnets will only be cleaned, they won't be replaced. So they're stored in the high activity cleaning area, while other components are taken out and stored in long-term storage. That blue piece there is a containment shield. So as you can see, a component of the tokamak comes out, containment shield goes on, and this will aim to prevent spread of radiation and tritium throughout the whole plant. And then the whole reactor comes apart, goes into the temporary storage area, and then these components will sit for a period of about 18 months while their radiation decreases. And as I mentioned before, in the high activity area, you've got some of the support structure, some of the lids, and some of the magnets. We'll then navigate the new components from the assembly area to reconstruct the tokamak. So that's it going back together. And then finally, the components that have been stored for 18 months will then be moved to a dismantle area, because there'll now be a low enough radiation that the robotic manipulators can get in there and cut them up into pieces. And then they'll eventually be moved off to a waste processing facility where they'll sit for many years to become deactivated. So that's the overall maintenance strategy that we'll be performing every 4 years. So what do I do as a graduate design engineer at UKEA? Well, I've been working on developing the remote maintenance tasks you saw in the previous video. We're trying to streamline and find bottlenecks in the process to reduce the amount of downtime of the reactor, and that will help us be more profitable in the future. I've also been involved in lots of CAD work. On the right here, you can see a picture of the CAD for the vessel, and I've been working on pipe routing routes and redesigning the vacuum vessel geometry. I've also been doing a work package on the maintenance facility optimization. So the whole building you just saw is just a concept, and at the moment we're trying to figure out a way to better design and minimize space, because every building that has to house radioactive components has walls of concrete that are multiple meters thick. So if we can minimize the amount of footprint we need, we can massively reduce costs for STEP, which makes it a lot more appealing for potential buyers. I've got a future work package coming out, which is analysis of components. So I'll be doing computational simulations for structural and radiation analysis for STEP components to try and predict how they'll react. Yeah, and that's everything. So if you've got any questions, I don't know if we'll wait until the end or if you ask now, but I think that link goes to our website if you want to find out more information about STEP, and my email's there as well if you remember anything afterwards. Thanks, everyone.
Thank you a lot, Elliot, about your presentation. It was very enlightening and very nice to know about all the plans and how you guys are going to do the maintenance work as well. Thank you. So yeah, guys, if you have any questions for Elliot, you can put them in the chat and he can have a look and reply as we go through our second presentations. But in the end, after the second presentation, we're going to have a panel, a Q&A, when you can talk out loud if you want, or put more questions in the chat, and we're going to have a conversation going. So cool. So now then, it's my great happiness to introduce the second speaker. So our second speaker is Prashant Dwivedi, Ph.D. student in the Advanced Material Science group at the Czech Technical University in Prague. working under the supervision of Professor Tomas Polcar and Alberto Fraile. Previously, Prashant obtained a dual degree Mechanical Tech and MSc in Sustainable Nuclear Energy and Waste Management from the Ecole de Mines Nantes in France. For his master's thesis, he worked at the Institute for Magnetic Fusion Research, part of the French Alternative Energies and Atomic Energy Commission in Cadarache, in collaboration with Japan's National Institute for Fusion Science. Prashant also previously worked as an intern at the Plasma Research Institute in India, where he investigated the role of surface roughness for coating parameters for the magnetron sputtering unit. And later he joined the Belgian Nuclear Research Center, SCK-CEN in Mol, funded by the Horizon 2020, as a student researcher working on the parameterization of the kinetic Monte Carlo model to simulate microstructural damage. His current research focuses on the atomistic design of nanoscale metallic alloys, and his trajectory includes the publication of impactful work in journals such as the Physical Review E and Nuclear Fusion. So, Prashant, whenever you're ready to start your presentation, we are ready for you to.
Hey. Slideshow, share. So I hope you can see my screen now.
Yes,
Okay.
perfect.
So, okay, I'll start, and thank you so much, Anna and Eloy, for a really nice presentation, and Anna for a really long introduction. But yeah, today I'm going to talk about one of my work, which I'm doing during my PhD. It's about investigation of dust wall interaction using molecular dynamic simulations and for the fusion devices. So I'm working with Alberto Fraile in Bengal University and Giovanni Boni from SCK-CEN and Tomas Polcar here in Southampton University. So I divided my presentation in 4 main parts. So it's a little bit more technical, but you can ask me any questions if you have any doubt in the audience. So I'll start with a little bit motivation and then method for my molecular dynamics simulation and some results. And based on that, I'll conclude my slide. So as already we know from earlier presentation that the fusion power holds the promise of clean and virtually limitless source of energy. And unlike the traditional power source, fusion power has like no greenhouse gases and generation of no long-lived radioactive waste, and which actually make it for good and environment-friendly options. And we also have the abundant fuel sources available worldwide. So fusion have the potential to revolutionize the energy production on the large scale. And perhaps we can see for most important part is it's an inherently safe process, and which make it for a promising option for the fusion energy needs, what we will have. So if we go for the root of fusion, so as I said that despite the promise of fusion energy, there are still several significant challenges. If we see for the roadmap for the ether and demo, we will have about the these Q factor which Eloy was mentioning. So here we are expecting for the 10, and then our plasma will be from 300 to 500 seconds. But then we will also have like these 3 dPa. It's about the neutron damage, irradiation damage. So we will have these things on the material. And if we go for more fusion reactor, the practical one, so we will have really high neutron dose. And apart from these, we also have really other material challenges which need to be addressed before what we were actually trying to achieve. So if we go in more detail, so as I mentioned, plasma material interaction is a crucial issue in realization of a practical fusion power reactor. And controlling plasma wall interaction is important because it's actually really the main ingredient to achieve the high performance. So the interaction process between the burning plasma and the first wall in the fusion reactor are like really diverse ones. So here, this is the one pulse from CCF in UK. So from the Czech Tokamak, so you can see here really the bright spot. And this is actually where the first wall will be exposed to really extreme thermal load of up to several tens of thousands of megawatts. per square meter during the operations. And that's why we need to have like a selection of a material which can adhere these things. So for the moment, tungsten is considered to the most reliable one material for high heat flux components. And why? So we already know that it has a high melting point. It's up to 3,400 degrees centigrade. And then for the high thermal conductivity. But there are so many processes happening inside this tokamak vacuum chamber. So you can see here, these are the processes which happens, and in the scale of this picometer to nanometer scale. And if we go for time scale, so from picometer to microseconds, there are so many processes happening. And actually, it's like plasma sputtering, then flaking, and the redeposition of these layers, and then melting, which cause small dust particles. And these dust particles actually reback as an impact on the vacuum vessel wall. So these actually have really hazardous, and I'll say that is due to the potential of explosion and radiological defects, what will happen. So there are so many studies done on it, experimental one, where they reported that it can go the dust particle have a velocity of about 500 meter per second to 1,000 meter per second. And most of the studies are experimental. So it's like a postmortem one when we have these dust, and you can see here with these references. So we can see here that these are the dust, and you see that the crater formation of this vacuum wall and these things. And here, these are the three images about from fast camera, where we can see the dust trajectory and also like how they actually move inside the vacuum vessel. So most of the studies are done from the plasma side, and also dust code, which is well known, those who work on these dust dynamics. So it's as done, but then there is nothing which comes out from the material side or some atomistic simulations to see how this mechanism actually making changes inside the material properties. So that was the motivation to start with. So I started with molecular dynamic simulations for doing the theoretical study from the material perspective. So going towards the method part, I will like to give just introduction about what was my sample size and these things. So my sample contained around 100 million atoms, and we did it for two these projectile size. Still, I said the big and a small, but a small one, if you see from the real perspective of a dust size, what we have is in a micrometer, but there are evidences where we see that there are some nanoscale dust. So here, these two, big and small, are constituted up to something around 4 nanometer to 8 nanometer. And then we went up to velocity of 1 to 9 kilometer per second. And we give our simulation time is something about 0.1 femtosecond, which is actually, these time steps are really important in molecular dynamics simulations. So here 0.1 femtoseconds is well enough to small to conserve the total energy, and especially in the beginning of the simulations. And then we went up to 200 to 200 picosecond because we wanted to track the dislocations, and it's sufficient enough to see the fast increase in dislocation densities, which is material defect, line defects. So dislocation densities, and to see also the recombination of it. And doing so, all these things, we actually use lamps. Is well known in computational material science community. People used for the molecular dynamic simulations. And then we use Ovito, which is actually an open source visualization tool, which you can use for about to see the extract all the data from lamps, and then you can see the atomic trajectories and all these things by this software. So one of the main ingredient before doing the molecular dynamic simulations always come is about the interatomic potentials. So for this work, we choose the two potentials. One was Marinica, and this is the name of the guy who developed it. So Marinica and Olsen. So our choice of potential is based on that we will have the real agreement for the plastic and point defects for the first one. of a material, and then we went for choosing other one is about because this force field was fitted to Rose equation of state, which is actually important when we have these high pressure simulations, and which will have this in this case. And then we joined our two potentials by this ZBL, which is actually universal repulsive interatomic potential at a small interatomic separation distance. So we use this ZBL correction to do it. And then going for more, as I said, that we choose these two potentials. So these are some material properties which I calculated from these two potentials and then compare with the experimental one. So we can see here a little bit differences about the melting point and then prediction with these two potentials. And then also about the enthalpy of melting, delta H here with the experiment. So you can see here that it's actually really low. So what it means that if we model our system with the Olesen potential, it will actually melt easily, not in terms of lower or higher melting point, but in terms of this melting point enthalpy, delta H1. And if we see more looking for the Rayleigh distribution function, so it seems that the liquid present in both the structures are quite well represented with the both potential are same. So going for the result part, here is I'll say the main picture of all the processes in what stage it happened about these impacts. So the first, I'll say the first primary stage of this is actually like a phase in which the period during projectile act as a contributing the force, while its kinetic energy is impacted to the target material, and it's same as like a fluid flow or hydrodynamic process. And if you go for the second phase, where the very dense and high pressure region releases is like a radially one, and then the formation of these semi-spherical earth crater, and all these material actually fly away, and they like in a vacuum, and they make this cavity. And then the third phase is like corresponding to the equilibration and recombination. So where you can see that these dislocations which were formed in the earlier two stages, now they get recombined, and these dislocations are like moving, not making further new one. They are recombination, and there are no new production of dislocation happen. So it's like an equilibrium phase of whole this process of impact. Then this is just a nice video to show you what's happening inside. So these small dust particles, they hit the plasma facing wall or the diverter part, and then you can see here this cavity formation, this crater formation, and all the particles which is flying around is the sputtered atoms. And inside the material, you see these are the line defects, and these two color actually shows that the two type of defects dislocations, so like the screw one and the edge dislocations here, and then making it in a graphical and number form. So here we are seeing that the volume of the crater is calculated from the number of atoms which were missing below the surface. And as we can see here, these crater from the Olesen potentials, when I use, it's actually more deeper. And these differences are likely when I said about the various properties of tungsten, liquid tungsten, depending on the force field. So that's why it's more deeper one here. And we can fit this whole volume in the linear dependence form with the kinetic energy with these equations. Then going for the other results, it's important quantity that the number of ejected atoms, we so-called ejecta in our terms. So the ejected atoms are those which are actually crossing the surface of the target, and which were not considering these crater formations. So they are actually really flying away. And as we can see that the number of atom increases with kinetic energy, and we can fit these things in a parabolic curve, which appropriate looking at it from the small to big. And these are some equations. I will not go into too much detail, but these are the equations by which you can fit these sputtered atom, how sputtered atom versus kinetic energy. And then one more important part is it has to be noted that how much atoms getting implanted in your real material there. So it's actually like we presented here the percentage of these atoms versus kinetic energy of the projectile. And as we expected, when the velocity is low, the almost all the atoms are like implanted in the main surface or substrate of the material. And in other words, we can see that the projectile slightly penetrates and adhere to the target without causing like any damage like this crater formation. But for the higher kinetic energy, we can see that the number of impacted atoms actually get a little bit decrease, and such decrease is because more they are actually getting out. So we'll see the more noticeable for the small projectile. Then the other part is about when I was mentioning about the total dislocation. So here I actually plotted this total dislocation length versus time that shows the main damage occur when the first movement happens. So you can see here most of the damage happened at the time of this 20 picoseconds. So here you see the really lot of dislocations they actually generated, and after over a time these get reaching almost like a constant value up to 100 picoseconds. So this is the video of like when it get impacted. So you'll see it start with really lot of dislocations, whole forest of it. But over the time, these atoms getting flying away and these are getting recombined. So we will left with some dislocation loops, which are really highly mobile, and some of them are stable one. And then the other part is to see this total dislocation length versus kinetic energy one. So as we can see here from the figure, it's a linear relation which found in between these two quantities. So it's similar relation which we seen earlier in the crater and the volume of kinetic energy. So we can make an assumption that this relation shows that the least the part of the crater formation is related to the dislocation formation, and therefore the plastic deformation of it. So then it's about the study which I'm doing now, because all the studies what you've seen, it's about the single crystal. So but in reality all these materials will be polycrystalline. So you can see that just one example how these crater and all these crater volume these depends about the orientation of the grains, and also about the velocities, and also the impact angle of it. So now to just conclude of what I shown you, so we did the molecular dynamics simulation to see high velocity impact in tungsten, which is actually mainly used in these devices now, and also in future we are trying to use tungsten alloys for it. So our simulation actually gave us about the extraction of this quantitative and qualitative information, which actually shed the light, I'll say, in the complex phenomena was happening around there. So, and these principal results is that the energy of the projectile is partitioned into dislocations and sputtered atom and really extensive surface deformation, which we seen like as a form of crater, and which is relatively amount in the being more dependent to projectile size. And some of these are like other properties are mainly for the dependent on the force field what we used. And if we see for the more application part of it, rather than the fusion devices here, the same thing happened on the interstellar projectile when it had hit to the spacecrafts. So we can use these studies to implement there how these all these big particles hitting to the spacecraft and making the crater formation, and to see what we can do for that, and then prepare our materials according to that. And if you wanted to see more like more work on it, so one of the research is published one, and another one is actually we are on the review process, where we try to do our make a model of this crater formation, what we have seen with the projectile, to see in the form of geometrically necessary dislocations in a theoretical perspective. So something like these craters formed with the impact to relate with the indentation process. And if you wanted to see some more videos or know more about it, you can see the LAMPS page where I published it there. And once again, thank you so much, Anna, and everyone for listening me and giving me time, and also the organizing committee for giving me the chance to talk about my work. Thank you so much.
Thank you, Prashant, for your presentation. It was very interesting to see how you do your simulations. Very nice. All right, so now audience, we will be opening our Q&As panel. So our panel is the opportunity for anyone to ask questions to our speakers, either about their research work or career path. So questions can be about nuclear fusion, about science in general, or about their careers too. Disclaimer, you do not need to be a specialist in nuclear fusion. We are not expecting you to be one to ask questions. So all questions are welcome and help to initiate a conversation on the topic. So you can type any questions on the chat, or if you want to talk out loud, you raise your hand and you can open your mic. And the speakers among themselves, you can ask questions to each other as well. And yeah, so we can start this then. So while we wait our first question of the day, I do have a question for the speakers. So we do have lots of different types of energies, right? Moving forward, if we don't want to, continue to use fossil fuel and all that, we have the hydro, have wind, we have a lot of stuff, cool stuff going on. So I'd like to hear from both of you, what made you guys decide to, study or work with nuclear fusion, with fusion energy? What is about fusion energy that excited you both? So if we can start with Elliot first and then move to Prashant.
Yeah, well, I think the important thing about fusion is it's a global solution. We're in a privileged position in the UK where we can actually produce a lot of our energy renewably using wind and tidal renewable energy. There's a lot of countries in the world that don't have access to these weather conditions, and obviously the sea as well. So it's about coming up with a solution that's viable not just for Western countries but across the world. And then obviously you've got the benefits of it being green, sustainable, and much lower radiation waste than with fission.
Lovely. And Prashant?
Yeah, so if I comment on this, I actually, that's true that we are working for different perspective to get the energy as renewable energy from wind one or the other solar power and everything. But we have to understand one thing, that the energy need, if you see, there is really nice graph from the OECD report that if you plot the energy need for the more 100 year in the future one, so you see there's a really big gap which you cannot fill by just going for the renewable or the conventional energy method what we have now, like the fusion one or fission one, sorry. And to fill this gap from the fission and stacking over all the renewable one and everything, but it's still there a really big gap which you need to fill by a really reliable source and which can give you really lot of energy to fill this whole parameter. And the fusion really fit on that. And that's why I will not deny that we have other conventional method plus the development one about the batteries and all the renewable one. But for the industrial scale, you can just imagine that in the industrial scale, you need really high power to run. And also the domestic need what you have in the coming future with the population increasing day by day. So that part is something fusion can really work on it. And also there are some challenges about the material and everything, but if you see the back history, the fusion was developed earlier than the fission one. But then the challenges is just about the physics and these things to get the output of it. So that's why it's really important to work on it, that we have to achieve the fusion one, but we have to work for the fusion one. And when we have already proved all the physics of it, but only the problematic part is the engineering perspective of it to develop. So, and we are very close. So yeah, always there is say that the fusion energy is 50 years away, but now I think it's not 50 years away. It's really near, I would say. So yeah, this is one just I wanted to comment about this energy need, what we have for the near future. And we need to really rely on some I'll say the fusion like the nuclear fusion power, which can fill this gap. So that's that.
Yeah, the physics is definitely there. It's definitely the engineering that needs to catch up.
Exactly. Exactly. I have one question for you, Eloy. Actually, when you're showing about the waste management part, so I'm actually not sure what material you are using for whole step. I think it's the same tungsten and tungsten alloys and everything, which we already know from ITER and JET and everything. But my question is, when you said about the 4 year, about then it will go to some waste management facility and maybe something like resting period before it can go for this radioactive waste. But this, which kind of waste it was? It was like a radioactive waste, or and if it like this, my first question is it like a radioactive waste, or if it's a radioactive waste, then how much radioactivity it was, like 10 year, 20 year, or something like that?
So are you talking about in the temporary storage where it sits for 18 months?
18 month.
Yeah.
And so 18 month, but it also depends on the material what you used, because something like if you have a tungsten which is irradiated like a really little bit, even then it has like a radioactive of something 10 year of scale.
Yeah.
So 10 to 20.
The 18-month value was taken from allowing the components to get down to an appropriate level where robotic manipulators will be able to come in. Before this point, they won't be able to do any work on them because the gamma radiation and the neutrons would just destroy the circuit boards and electronics. And I think based off the half-life of some of the materials we're using, after 18 months, there's a considerable decrease in the radiation levels. And after that, although it keeps going down, it's going down at a lesser rate. So that's when we can come in and intervene, dismantle it, put it into ISO containers, and then it will go to its long-term storage, which will be, as you say, some of these half-lives of many, many years for them to deactivate.
Okay, and so which material it is? Is tungsten, tungsten alloys, or if
Yeah,
if I just
there's
consider for
steel,
vacuum vessel?
tungsten alloys. I think there's something called Urofur as well, which they're hoping to use. But again, we're still in the concept design stage, so even the materials are still being considered. But yeah, definitely we'll take lessons from ITER and JET and use like.
Okay, and so when it's planned to start like building it?
I think construction is expected to start in the late 2030s, and then commissioning can start in 2040.
Okay, and it will be like if I put it in scale of it will be like something like demo, or it's a fusion reactor like commercial one, or
size-wise?
Sorry?
Do you mean size-wise?
No, not about the size-wise. I'll say about the main aim for this step. So its aim is to demonstrate the commercial energy, or still it will be like the research like ITER. But I think
so. Its aim is to prove that we can produce net electricity out using fusion. So there'll have to be a high enough Q factor, far higher than ITER's, with all the losses when you're in the heat exchangers and power that needs to power for the buildings. That's all going to be considered, and we need to prove that even after all this, there's still a net electricity output. So it is a science experiment, but it's to, like demo, it's to prove that we can do it commercially.
Okay, so
it's kind of like a demo and step have the same date of completion, I think 2040. So I guess it's two ways of looking at the same problem, Instead, we have vertical maintenance where we're bringing out components one
Yeah.
by one, and in demo, they dismantle the components through radial access in small segments. So I guess it's two ways of looking at the same problem and trying to prove that we can get to the same point.
Okay, that's nice. Thank you.
Lovely. Well, we have a question from the audience. So Cheng Fan Wood has a question for Elliot. Cheng, thank you very much for your question. So he says, according to your idea, does the fusion reactor could be smaller or easy to maintain in the future? And how close of this to the future?
Okay, not very close, unfortunately. Our initial goal was to make steps smaller than ITER, so it was more manageable, but the plasma physicists have done all their computing and it's actually going to be larger. And it seems at the moment to produce higher Q factor, you need larger vessel volume. So we'll have to keep looking at that to see how we can modularize and make fusion reactors smaller. But for the minute, I think that large seems to be the solution that we're looking at.
Great. We have another audience question. So David Giles is asking to Elliot as well. How does the maintenance of fusion reactors compare to typical fission reactors?
I don't know a huge amount about fission reactors. I watched a documentary recently with about fusion reactors. The guy that does I forgot what his name is now, but they went into a fission reactor and they have a lot of the similar robotic manipulators we have on site in Culham. So there'll be an actuator which a remote handler can use to control a robot arm and handle radioactive waste. And that was shown in the fission reactor, and that's what we use in fusion. So there's a crossover in that sense. But I'm not sure about dismantlement of fission reactors or if that's similar to fusion at all. It was Guy Martin, that was the documentary. It's good if any of you got some time. It's a good overview of where energy is going and the comparison between fusion and fission.
Great. All right, so while we wait for more questions from our audience, I do have a question for both of you. I'm not a specialist in nuclear fusion or fission at all. I study batteries and that's my sweet spot. So my question is like a broad one. So when usually we start talking about nuclear energy, right? We always feel there's like an elephant in the room, especially for people who do not work in the field, because you know the conversations are that people are usually scared, right? Maybe because of movies and sci-fi fiction and stuff like that, right? So what I would like for you guys to tell us and tell our viewers on YouTube as well is like what you guys who work in the field would tell people who are skeptical or afraid of nuclear fusion, like why is it important to keep going down this field and how safe it is nowadays as well compared to other energy like sources and experiments and stuff like that. So yeah. So any of you can start.
Prashant might know a bit more about this than me, but I believe that the actual reaction of fusion is inherently safer than fission in the way that you can't really have a spiral chain event in the same way, because we have these pellet disruptors we can fire into the reactor to basically halt the reaction instantly. So it's much more controllable. And in general, I know people always bring up Chernobyl, and a lot of people don't understand the difference between fission and fusion, and they hear nuclear and think, oh, bombs and like it's going to explode. But regulations have come so far since, like, for example, when Chernobyl happened, there's so much more safety rigmarole and stuff that you have to go through. So we are in a different time. Even fission reactors are far safer, but I think fusion as well as a reaction is more controllable, I think.
Yeah, exactly. If I try to just add on to Eloy, that's true. Actually, I think it's just because from the historical point of view, what happened, like this Chernobyl and everything. So these went like really all over the world, and it was actually worst disaster ever happened. So people know. And then Fukushima. So that's why people are scared when they just see the word nuclear, and even the government bodies when they see the nuclear. So we have to really understand that that there is one perspective of it, if I put it like that, that the world's safest place is a nuclear reactor where you work. If you compare with just walking around the street, because you can die in the street rather than the nuclear reactor. So this is the safety level, what we actually really do in the nuclear reactor, actually, when we work. So it's the safest place according to the safety rule and protocol and so many other things. It's really, really rigorous one. And then if I just compare about the fission and fusion, as Elliot mentioned, that true, in fission, it's like we really do it controlled way and everything. And there, the possibility of everything, like anything go wrong is just 0.0001%, which actually happened in some time. If you see this, all these biggest disaster happened in last 50 years. So these fission one, if you compare with the fusion one, here, what happened that when you have this whole plasma, the maximum what can happen is like plasma is disrupt. You will have no plasma, and so no fusion at all. So it's like there is no radiation coming out, something like that. When you create a really high dense plasma or all the things, only then you can extract these high energy neutron, which actually generate the electricity and everything. But the most hazardous part will be it will not be going to blown up, because if any parameter of this making plasma is going up and down, then plasma is erupt and there is nothing left out. So there is no blowout like the fission one, where when you have your reactor pressure vessel, when it has like no coolant, or you do not have a power backup, which happened in Fukushima, because this whole power backup of the generator was already drawn in the flood. So they do not have a power backup to cool down the vessel, and it actually really melted. And this is the really, really like, I'll say, not everyday job that you can melt the power vessel. So it's really, it takes so much disastrous and everything. So yeah, if we compare for the fusion, in the fission part, so yes, fusion, you will just have no plasma and no energy and no blown up, and everything is like nothing happening. And if you compare whole nuclear with the other safety procedure, as I mentioned, that the nuclear place is really safest one if you compare with walking around the street in any of the city, actually. So it's yeah, so safety wise, it's really, it's just the perspective how we think about it, because of all these historical events. So we have to really come up that to see the other positive side, because even the nuclear is used for the cancer research. And these are the nuclei what we use. We actually get more radiation when we fly. So in maybe 2 times a vacation. So I really put it low 2 times, but yeah, we have many vacations. So yeah, so we get more radiation than in going for the flight. So if you see in this perspective, it's really low, and we can always use the positive side of nuclear fusion or fission energy.
Yeah, there's a fun fact of my work that the employee that sees the most radiation of anyone isn't any of the people that work on maintaining the reactor or in the Tokamak building. It's actually the CEO, because he's doing the most flights abroad
Exactly.
to the conferences and stuff.
Exactly. While promoting the fusion and fission, we get the more radiation.
Yeah.
So yeah.
Wow, that was very insightful, guys. Thank you so much. We do have another question from our audience, possibly our last question of the day because of the time. But so Cheng Feng Wu is asking for both of you a very optimistic question. In future, do we have the possibility to bring the fusion reactor on board the ship? What do you guys think?
Do you mean like how we have fission reactors on submarines, things like that?
Okay, summary.
think there's whatever.
Yeah.
I do think we're still at the point. Let's put it this way: we can't even produce electricity with it yet at the scale that it's at, with all the remote maintenance tasks. So I think we'll have to. We're so limited by the size of these reactors and how large they have to be at the moment, and it's still so conceptual that maybe in the future one day, yes, but I think it's very far away.
Yeah, that's true. I'll say that, okay, from all the sci-fi movies and everything, I'll say yes, it's possible, because nothing is impossible. We are researcher and engineer, we can do that. But put it in a serious way, actually there are work where they are making fusion power for the rocket engine. Like this will be generating the energy to give the thrust and everything. They are working on it, but yeah, when I said the only problem is to get the maximum energy first. If we achieve that, how much we put to generate the plasma, and once this hurdle will be achieved, because if we see from the, for example, if we see from the fission side, there we already are making the modular reactor, the small one. Like you can have for one city, we will have a small modular reactor, and it's really progressive one. And maybe in coming year, we will see that. So same thing, because in fission, we already know all the physics, all the material challenges, all the engineering challenges. So we are building it to more small, compact and everything. And same thing here, if we apply for the fusion research. So once we actually do all the part, like engineering part and all these hurdles what we have to generate first the energy, like this is Q factor, will be really large. So maybe who knows that we will have this small fusion reactor in a boat, or these are actually powering our the rockets and everything to going to the Mars. So yeah, that's true. We have to be visionary to see that. So it's possible, I'll say. I will not deny it, but it's still, there is a lot of challenges to work on it.
Right, everyone. I love how big and creative everyone is thinking today. Lovely. Well, because of time, guys, I would love to keep going this conversation, but because of time constraints, we're going to conclude our Q&A sessions. And yeah, Cheng is saying your idea is much bigger than me. Great. So we conclude our Q&A session and webinar. I would like to thank greatly our both speakers today and our audience as well for keeping the conversation going. It was lovely to hear about UK plans, how we maintain the reactors, how we simulate things inside a reactor. And, you know, it was a lovely conversation. Thank you, everyone. And well, just, you know, if you want to keep up with our next webinars, we're going to have webinars about batteries and maybe about hydrogens again, tidal energy. So keep in check on our social media, or put your emails in our chat now, because then we, you know, we can put you on our mailing list. But yeah, just keep up with us, and it's lovely to be able to talk to everyone and just promote excellent research and excellent energy sources. So thank you, everyone. Everyone have a great Wednesday and holiday period as well.
Thank you so much, Hannah. And
thanks for your time, everyone.
Thank you, everyone. Yeah, it was